So you've seen in the previous section how taking the derivative of a natural log becomes 1 over argument, and of course times the chain rule. So the derivative natural log of u would be 1 over u, that's the derivative of the natural log, times u prime, which is the chain rule at work, so it would be u prime over u in the end. How we got there was actually by integrating under the 1 over x curve. If you remember, that's how we actually figured out that there must be something more to integrating that particular fraction than the power rule, because the power rule didn't work. So now we take advantage of that knowledge, and that is that since the derivative natural log becomes 1 over argument 1 over x, or the derivative natural log of x, then it goes the other way. The antiderivative of 1 over x must be natural log. So let's take a look at the log rule for integration. This is from section 5.2. And the log rule states the following. If you were to integrate the pattern 1 over x, here's what you do not get. First of all, this, by the way, is equal to x to the negative 1 if you want to write it that way. But it is not equal to the power rule. You do not add 1 to the exponent and divide by the new exponent, because basically, look what you get here. For the most part, if x is not 0 itself, you get infinity. And that is not the area underneath the 1 over x curve. That's a big failure. But after looking a little more carefully at integrating under the 1 over x curve, we learned that it ends up being the natural log of that x plus a constant. Now, when we create a natural log using the integration process, we want this answer to work a little more often than it normally would. What I mean by that is, if you integrate 1 over x and you happen to be over in negative x territory, well, there's still an area, and without the absolute value, the log rule wouldn't work. So 1 over x looks like this. It's a curve that we have a piece here, and we also have a piece here. So what if I said, I'd like you to integrate, and normally we integrate from left to right, so I want to integrate from negative 2 to negative 1, and I want the area between the curve and the x-axis. Now, if we look down here, this is the 1 over x curve, and the area is right here, and the area would be negative because we're in a space below the x-axis. Let's try to integrate 1 over x without using this protection of the natural log, the absolute value of x. What would happen? Well, the integral of 1 over x is the area, and we integrate from left to right. So we're going to start at negative 2 and stop at negative 1. And if there was no such protection, you would get this. The natural log of x, negative 2, negative 1. The natural log of negative 1 minus the natural log of negative 2. And that doesn't work. So it can't just be plain natural log, because the area computation is coming out undefined. You remember the natural log function only works for positive x's. In some ways, it's like the square root function in that sense, in that natural log doesn't work for negative numbers. The domain for natural log is x is greater than 0. Not greater than or equal to 0, but greater than 0. In fact, let's take a look at the natural log curve. The natural log curve is a reflection across the y equals x axis of e to the x. So if we put a little dashed line here, we can write y equals x. E to the x is an exponential growth curve that looks something like that. And the natural log is the inverse of that. So we reflect across and we get a point. We reflect across, we get a point. Reflect across. So this curve looks more like something like this. And this is our natural log curve. And I think you can clearly see that it just doesn't work in negative x territory. I'll bold it up. This is the curve. And where does that curve operate in negative x territory? It doesn't. This is 1 right here, and this is also 1. So the natural log by itself doesn't seem like it's delivering the goods for negative values of x, although there's an area over there, and I would prefer that our integral produces the actual area, the result. Now it's a negative area, so it should be negative, but right now I'm not getting anything because I'm doing the natural log of negative numbers. So what does the natural log of the absolute value of x look like? Well, whereas the natural log of x is a curve that looks something like this, the natural log of the absolute value of x says, well, you know, when x is negative over here, the absolute value will make what's inside positive, and you'll just get the natural log of that positive number. In essence, what it does is it creates a reflection across the y-axis. So you're going to get something that looks something like that. So this curve right here is the natural log of the absolute value of x. It's got, when x is positive, we get the old natural log of x curve, and when x is negative, we get this reflection over here. So now it is producing, in fact, the only place where you can't seem to get an answer is the natural log of 0. So let's try applying that to the area under the 1 over x curve. But let's run that from -2 to -1. So now, when you produce a natural log through integration, now you need to remember that you want to protect it so that it works a little more often than it normally does. See, this is what it would normally operate. Natural log of absolute value actually works over here as well and produces y values. Now we want to run this from -1 to -2, and so therefore the answer will be the natural log of -1 minus the natural log of the absolute value of -2. Well, thanks to the absolute value symbol, we're able to do this. Now the natural log of 1 is 0. It's right here. Natural log of 1 is 0. There it is, right there, 0 for the y value. So it's just minus the natural log of 2, which is minus 0.693. So in reality, you are able now to integrate even on the other side, where there really is an area, happens to be negative, but you are able to integrate over there and get a result. So here is the reality. When you integrate 1 over x, the power rule is a complete failure. We're getting infinity. It just doesn't make sense. Turns out we learned that the answer for the integral of 1 over x, that one undoable integral that uses a power, that's the only one that doesn't work, through discovery we realized that it is the natural log function. Now when you create one using integration, we want to protect it. So let's protect it with an absolute value. And that makes it work more often than it normally would, but we want it to work more often, as you saw from that problem. So what do we do when it's not 1 over x? Remember when we integrated x squared? That was pretty easy. It was x cubed over 3. And then later we were able to integrate other things that were cubed. And the reason we could do that is because we had integration using substitution, or we had the key or evidence method, and we realized that there was a way to do that. The same situation holds true here. What if it's not 1 over x? What if it's 1 over 4x? This will be an indefinite integral, no limits of integration. Well, this one, you can just take that 4 and slide it out front. It's actually a 1/4, and it is actually integrate 1 over x. So it would be 1/4. This becomes the natural log of the absolute value of x plus a constant. And in fact, because it's a logarithm, logarithms have all these special properties, we very well could, if we wanted to, plop this up as an exponent. So it would become the natural log of absolute value of x to the 1/4 power plus a constant. Or the natural log of the 4th root of the absolute value of x plus a constant. All valid answers. So this function is going to work much more often than it normally would because a 4th power, very much like a square root, cannot tolerate a negative number inside and expect to get a real result. Well, there those absolute values are to help protect that from happening. So that's another good protection on the natural log, meaning it works more often than it normally would. But the reality is we need that because we do want to go over to the negative x-axis and we do want to integrate curves and get areas. So that was not very tough. The quarter just parked out front, but something unusual did happen. It allowed us to pop that up as an exponent, which a 1/4 power is a 4th root. What about this problem? Now that's a very different story. You can't just drag the quarter out front because it's really not a 1/4 constant multiple. If it was a 1/4 constant multiple, then this would be 4 as well. In other words, the 4 here and the 4 here would factor out, and then you can take it out front. So this 4, you really can't move that out front at all. So it looks like 1 over x, but it's not exactly 1 over x. So how can we make it look like 1 over x? Well, we're not going to make it look like 1 over x. What we're going to do is make it look like 1 over u. So if this is true, which we now know that it is indeed true, when you integrate fractions, they often produce logarithms. Who knew that until now? When you integrate a fraction, a 1 over x fraction specifically, that's the only one we're ready for, it produces a logarithm. And then if you take the derivative of this logarithm, you'll get 1 over x. So it does work. But what about this fraction? Do all fractions become natural logs? I'm not really sure. Now, if this is true, then shouldn't this be true as well? It's really saying the same exact thing. It's just that instead of having an independent variable of x, we have an independent variable of u. What if I was able to turn this into that? If I can turn the fraction into 1 over u du, then we've got our answer. It's natural log of u. So what we're going to do is we're going to shape our fraction and model it to see if I can make it look like 1 over u. I might not be able to, actually, but I'm going to try. So in this particular case, this is really u substitution. And for a fraction, a good choice for u is the denominator. Let's try it. Now, if u equals the denominator, we indeed will have 1 over u, but it still says dx. So that has to be replaced properly. I call this the full and complete substitution. The first part of the substitution is not such a big deal. I mean, we just called 4x minus 1 equal to u, so you're going to replace 4x minus 1 with the u. But to fully substitute, you need to deal with what's left. In this case, that is the toughest part, this guy. Now, how do you get that in terms of u? Come on down here, and you remember what I called this in the other chapter, autopilot, take a derivative. Every u substitution you ever do, I do need you to take a derivative du dx. Well, du dx is just 4. Move the dx to the other side. Let's see what we get. So now du equals 4 dx. Oh, that's pretty good, but come on up here And we're not quite there yet. So you already know about this part. That's a done deal. 1 over, that was u, right? Let's double check. Sure was. U equals 4x minus 1. So that part's a done deal. What about this part here? Well, just like all substitutions, you look down here to the derivative to find out what to do with this box, and I know what to do with that box. I found my box, dx. It is du over 4. So replace it with du over 4, and look where we are now. We're actually back to a problem we're pretty familiar with. Amazing. So we can forget that original problem. Can we do this problem? Well, we've already done that problem. The 1/4 will indeed slip out front. It's just 1 over u du, and we know the answer to that integral. Don't forget to integrate. It is the natural log of u plus a constant. And boy, if you want to, and I might ask you to take that constant and bring it up as an exponent, it would look something like this. And in fact, 1/4 power is really a 4th root. Now, this problem started with x's. You need to finish with x's. So let's see, what was u equal to at the beginning? What was the selection for u? Well, let's go back and take a peek. There it is, u equals 4x minus 1. So at the end of the problem, I need you to substitute back. And that is the answer to our problem. We have found the antiderivative. Now, one thing at the end of these problems, well, one thing, don't forget to always put plus c on an indefinite integral like that. Secondly, if you look at the absolute value symbols and you can free or release them, I want you to free or release them because that would be simplifying the problem. For example, if you had the absolute value of x squared, that's equal to x squared. You don't need absolute values when you're dealing with x squared because x squared is already positive, so we don't need the assistance of an absolute value. So I might look inside those absolute values and ask a question, and that is, does this expression in the absolute value always remain positive on its own? And if it does, you can free or release the absolute value symbols. Now, clearly x squared remains positive on its own. X to the 4th remains positive on its own. Sine doesn't remain positive, but sine x plus maybe 4, if you push the sine curve up a little bit, that does remain positive all on its own all the time. So you could release the absolute value symbols on that. So I do want you to release the absolute value symbols when it's called for, and that is when the contents are positive all the time by its own, under its own power. And another way you can detect that is by graphing that function and taking a look at it. That might help you determine if that's what you should do. Okay, so let's take a look at a problem where we actually take advantage of this to find the area beneath the curve. And I'm going to look at example 3 in the book. And example 3 asks you to take or find the area from 0 to 3 on this unusual curve. Hold on a second. That doesn't look anything like 1 over x, does it? It's x squared. And then there's an x on top, which I guess it kind of does look like 1 over x if you got rid of that minus 1, or plus 1. You can't do that, though. You can't get rid of the plus 1. So this looks pretty far from our 1 over x pattern or the 1 over u pattern. It really does. Well, first let me graph this, and then I think the first thing we should do is probably just get like a rough guess as to what you think the area is using the graph. So let's actually look down here at 1, 2, and 3 for x. It turns out that this function peaks at about a half, and that's right about here. And that's a half in y. And so it kind of rises up. It peaks at about a half. And then from there, it kind of comes down, but not so much. It comes down to about here. It comes down to about, roughly about 0.35 or something like that. So if you had to guess area on this thing, let's come up with a rough approximation. Well, the rectangle here, if we were to draw a rectangle, it's roughly, 1, 2, 3 times 0.5. It's got to be less than 0.5. So how much less? Not really sure, but I'm going to say that area is roughly 1. It's in the ballpark of 1. And that's just by eyeballing this curve, roughly. We know that the rectangle would be 1.5. We clearly have less area than that. How much less, I'm unsure of. I'm going to say about 1. That's a rough guess on this. And that's a good way to get started, to get a reasonable idea of how much area is under there before we do the calculus on this. So now we know that when we do this integral, we better be getting something close to 1. How do we do this integral? The interesting thing about this chapter is that it talks about integration and natural logs. But really, this chapter is about integration of fractions, plain and simple. Integrating fractions. And it's interesting that we don't have a quotient rule. We do not have a quotient rule, so we wouldn't write f and g and f prime and g prime. None of that will work for us here. But we do have a pattern that we've seen so far, that 1 over x pattern, or 1 over u pattern. Now, the guidelines have shown us that a nice idea for a u substitution on this problem should be the denominator. I think that's a good lead-in, and from there, I think you should be able to figure this problem out. So let's start with that and see where that leads us. Let's try that. Let's try u equals the denominator again and see what happens. U equals denominator would be u equals x squared plus 1. And I say try because it might not work. If you pick the wrong u and it doesn't work, don't force it to work. Try a different u. But this is an excellent guideline, u equals denominator. So u equals denominator, autopilot. Don't forget to do your du dx. So du dx equals, derivative is 2x. Move the dx to the other side. Okay, this is important. It's time for the full and complete substitution on this problem. What is my area? Now, from now on, nobody's going to get this wrong, right? X squared plus 1 from now on is the letter u, so we've got our letter u down there. That's done. It's this stuff that's left behind that's the hard part. X dx. What do we do with this x dx? And how do we replace it so that we're using our new variable u? That's where the autopilot, the derivative, comes in. Take a look at it right here. There's exactly what you're seeking right there. X dx is right here. So to isolate x dx, I would divide both sides by 2, and that tells me that du over 2 is precisely that box that you seek, x dx, and now you can complete the substitution. So instead of x dx, we're going to put du over 2. This is actually a 3-part substitution. The first substitution, u equals the denominator, not a big deal. Doesn't seem like it's too tough to do that. The second, you box up what's left, and it's always going to be on top normally. You box up what's left. You go hunting for that within the derivative. We found x dx sitting right here, divided by 2 to isolate it, and we replaced it with du over 2. And the last substitution. This says x equals 0 up through x equals 3. if you truly do the full and complete substitution on this problem, the beauty of that is there's no looking back. You don't have to go back to the world of x. Now, this only works for definite integrals in which you're looking for area under a curve, you're getting a number. So wouldn't it be nice if we don't have to look back at all that other stuff, that fraction, that difficult x over x squared plus 1 that we didn't know what to do about? It would be nice not to look back there. And here's how we do it. You're in the world of u down here. Let's remain in the world of u down there. In order to do this, you have to change the limits of integration into the world of u as well. So when x equals 0, plug it in here. Notice that u equals 1. When x equals 3, plug it in here. Notice that u equals 10. The beauty of doing it this way, and that is substituting the limits of integration as well, means no looking back. We don't have to look back to anything above that. No x's. We don't have to look at that fraction that we had before. We don't have to look at x equals 0, 3, none of it. It turns out that the area answer for this integral is precisely the same as the area integral for that one. Let's take care of this one right here now that we know that. So we don't need any of that. Blank page. We can turn the page and just work on this one. Well, we all know about that half. It's a constant multiple. Go ahead and bring it out front. And I want to show you what's left. Something very, very familiar to you. Ever seen that before? Of course you have. Integrate 1 over u, that's natural log. But it has to be 1 over u du like that. Okay? But we got it. U substitution saves the day. U equals denominator. The du kind of clears the numerator out for you. And you do and should get 1 over u, which is great because we can go right to the answer. 1/2 the natural log of the absolute value of u. Done. Calculus is over, except we want to plug in our 1 and our 10. Now let me show you a couple fancy things we can do with this. First fancy thing we can do is we can stick the 1/2 up as a power. And we still need to run the numbers through, right? The 1 and the 10. Well, 1/2 power is a square root. And we run that from 1 to 10. And square root really does require the protection of the absolute value to keep everything inside positive. However, we are putting positive numbers in anyway, so it really doesn't require the protection because the numbers are positive. But let's see what we get. It's the natural log of the absolute value, square root of 10, minus the natural log, square root of the absolute value of 1. Well, now we don't need the absolute values because absolute value of 10 just is 10. It's the natural log square root of 10 minus natural log of 1. But the natural log of 1 is 0. We've seen that on the natural log curve. It's right here. That's a 1 right there. It's the x-intercept, 1, 0. The natural log of 1 is 0, so the answer is the natural log of square root of 10. Or 1/2 the natural log of 10, whichever you prefer. It turns out that if you do that computation, this is what you get. That matches our expectations because I did look at the area under the curve by estimating and realized that it should have been close to 1, and it is close to 1. Had to be less than 1/2. There was no way to get this area to be larger than 1.5, and we didn't exceed 1.5. It was less than 1.5, pretty close to 1, which was our best guess. So that's how you solve a problem with U substitution. I also want you to know how to do the problem another way, and that is pure pattern recognition. It turns out that if u is a function of x, what you want to see on top is u prime. What you want to see on the bottom is u to the 1 power. If you see u prime on top and u to the 1 on the bottom, then the answer is the natural log of the absolute value of u. Now, I know before you're thinking, what happened to 1 over u? I thought it was just 1 over u. Well, if it's 1 over x, think about it. X is on the bottom. The derivative of x is 1, sits on top. If it's just a u on the bottom, that's true. U prime would be 1 on the top. But let's take a look for a moment at another problem here. Let's take a look at the one we just did. Without the limits of integration, let's just do this. What if you don't want to do u substitution and you want to use this new pattern recognition? I've got a 3-step checklist that will allow you to integrate a fraction and make it a natural log without u substitution. Step number 1, do you have a fraction? And of course, you're going to check that one off. Yes, indeed, I have a fraction. Number 2, is the denominator, or can you show that the denominator is simply to the 1 power? What about this squared here? Well, if you package it up, yeah, you can put a little 1 out there. So, yeah, I'll check that off. The denominator, I would say, is to the 1 power. And finally, the clincher, number 3. Is the derivative of the denominator in the numerator? Well, let's see if that worked. I want to see the derivative of this living on top. Well, what is the derivative of the denominator? The derivative of our denominator is 2x. So no, I can't check this off because that does not live on top. Well, you've seen me do this before. When it's an expression that I don't like, I fix it. This is actually part of the evidence or key method. So the 2x is actually the key or the evidence. And if it's not matching precisely, we can do something about it. We can plant evidence. So if you want the numerator to be 2x, which is what I want, make it 2x. So we're going to plant a 2 here. We'll call that the plant. And we're going to counter with a 1/2 out front. That will be the counter. So I multiplied by 2 times 1/2. I multiplied by 1. I really didn't affect the overall value of this problem. So can I check this off now? Yes, I can, because 2x plainly lives on top. Now, I call this the 3-step checklist, the 3-step checklist for integrating fractions. Now, I do see people use the 3-step checklist, and then they don't actually follow up on the payoff. So if you can check all 3 off, this is the payoff. The answer is, if you integrate that fraction with all 3 checked off, the answer is a natural log of the denominator, and that's it. You don't need the numerator as part of the answer because the numerator is part of the key or the evidence that never actually shows up in the answer. So, number 1, yep. Number 2, yes, to the 1 power. It has to be to the 1 power. It is to the 1 power if I put parentheses around it. And number 3, does the derivative of the bottom live on the top? 2x? Yes, it does now. Okay, let's get that payoff. Now, you know the 1/2 is along for the ride. That's not going anywhere. So what is the payoff? The payoff is natural log of the denominator. I guess we should protect it because we're creating a natural log. So it's natural log of the denominator. That is the answer. That's the payoff. And that would be the natural log of the absolute value of x squared plus 1 plus a constant. And here's one of those situations where you can get rid of the absolute value symbol. So yes, when you produce a natural log through integration, they always start with absolute value symbols. But if you can determine that the expression inside is always positive, you don't really need it. Superfluous, so we get rid of it. So x squared is positive, plus 1 more is more positive. Everything's positive in there. The best version of this answer, the most compact version of this answer looks like this. So I've given you two solid techniques for integrating fractions. Two very good techniques for integrating fractions. One technique is u equals denominator. Take your derivative and then find what's up there in the numerator with the dx. You'll find a replacement for that through your derivative. And the nice thing about that is ultimately when you get to the end, it'll simply say integrate 1 over u du pretty much every time. And then it'll become natural log of u when you integrate. So that's a nice approach. But the 3-step checklist is also very powerful because it works so fast. Number one, it's a fraction. You wouldn't even be thinking about the 3-step checklist unless it was a fraction. Number two, is the denominator to the 1 power? If it is, you can continue. If it isn't, then you can't continue. And number three, the clincher is, does the derivative of the bottom live on the top? And if it does, you jump right to the answer, natural log of the denominator. Now, let's test this answer to see if it really works. Will this actually reproduce that original fraction, which was actually x over x squared plus 1? That was the original fraction when we hit it with a derivative. Let's find out. This is how you check your integration problems after all. And let's change this to an exponent. Now, the lovely thing about natural logs, or any logarithm, in fact, is that we can diffuse the difficulty before we do calculus. We can take that exponent right out front and make it a constant multiple, which is much easier to deal with. Okay, now, there are other products for natural log. Inside, if there was multiplication or division, we could rip it apart and make it addition or subtraction, but we have addition inside, so I can't separate that any further. 1/2, along for the ride. The derivative of natural log, we have learned, is 1 over argument. Done. And what about that chain rule? Let's not forget our chain rule. What's the derivative of x squared plus 1? Isn't it 2x? And isn't the derivative of a constant just 0? Look what we just found. The original expression. It's pretty crazy, isn't it? The antiderivative of a fraction is a natural log. There's no chain rule. There's no algebraic answer. It's natural log. Primarily because of the way derivatives of natural log act. I mean, the derivative of a natural log is not a natural log. Derivative is 1 divided by argument, building a fraction, times chain rule, which will go on top. So it builds a fraction with something on the bottom and a derivative on top. So it's a good way to look at that. All right, I want to go a little further with this. And let's try one more where we did a 3-step checklist. So down here, I'm going to put, how about x to the 4th plus x squared. How's that? Okay. And here, I'm going to put 2x cubed plus about x. So we can do this two ways. We can do u substitution. U equals denominator is always a good idea. Or we could try the 3-step checklist. Let's try and start with a 3-step checklist. You're integrating a fraction. That makes me fairly suspicious that the answer will be a natural log. Number two, is it true that the denominator is to the 1 power? I suppose you could maybe almost always do that because you could encompass the bottom and show me that it is really to the 1 power. Now, where I wouldn't check this off is that if it already had parentheses, and the outer exponent was either squared or half power, square root, or something else. But this is a definite yes. And finally, number 3, does the derivative of the bottom live on the top? And the answer is not exactly. So let's fix it. Now the fix here would be to actually multiply by 2, and I do mean in its entirety, of course, and counter with a 1/2. And now I do have a match. Take a look what's up there. 4x cubed plus 2x works. So don't forget the payoff here. If you really check all 3 off, you can go directly to the answer. The 1/2 survives, and don't forget the payoff. It is the natural log of the denominator only. I did put the protection here of the absolute value symbols, but you know what? I don't think I need those. The reason I don't need those is because x to the 4th is always positive, x squared is always positive. Oh, and the 1/2 can come up as an exponent. Well, a 1/2 exponent, which indeed is a radical. The other thing to be careful of is, see this plus here, you can't really break this up quite the way you would like to. I know, I would really like to do the natural log of x to the 4th is x squared, or square root of x to the 4th is x squared, and the square root of x squared is x. Would really love to do that. Not allowed to do that. You can only do that if it were by itself or if it were a factor. I do see something sneaky we can do here. I'll accept this as your answer, but I just happened to notice something in there, that there is a common factor of x squared. Look at that. Bring the x squared out front. And isn't that interesting? The natural log, and this breaks up. And this by itself is just x. So in reality, there was a little bit more that I could do with this, but you had to look a little more carefully. So be careful with these sums under a square root. You're really not supposed to take the square root of each term. That doesn't work. However, if it's a product, you very well can take the square root of each term. Hey, there's one more thing we could possibly do here. Isn't it true that the natural log of a product becomes the sum of 2 natural logs? So, some interesting stuff here. Although I think I broke the function. How did I break the function? Well, the earlier version of this function right here worked perfectly for all values of x. Even negative x's work fine. Let's pick like -1, put it in there. -1 to the 4th is 1, plus -1 squared is 1 plus 1 is the natural log of radical 2. Not a problem. But look at the version I have down here. -1 goes in here. That's the natural log of the square root of 1 plus 1 is 2, no problem. And natural log of -1, that's undefined. So that one's tricky because in order to be correct, I guess we have to reintroduce the absolute value symbols because now the function is broken again for negative x values, and it's not supposed to be broken. So very interesting how that one evolved. Now I've got some other things that I'd like you to look at, and that would be a problem like this one. Okay. So we get through doing this and we almost think that every fraction integrates to be a natural log. That is not true. So what I need to do is emphasize the 3-step checklist. So let's do the 3-step checklist on this problem. Really run through all 3 steps. Number 1, is this a fraction we're trying to integrate? Of course it is. We wouldn't be using this checklist otherwise. Number 2, is the denominator truly to the 1 power? No, it's not. So you can stop right there. I don't think we can go any further with the three-step checklist, and that leads me to believe that this probably is not a natural log. So, all right then, how do you solve it? When the denominator is not to the 1 power, here's what we need to do. Make it not a fraction anymore. Push the bottom to the top and see what happens. Now, if we push the bottom to the top, what happens here? This bottom comes right up to the top and becomes x squared plus 1 to the negative 4 power multiplied by a 2x. And we're back to the previous section. Now, you can do this problem one of two ways. You could do U substitution if you want, or you can do the evidence key method. They both work just fine. Let's do both. Now, what I see here is the more complicated function here, the less complicated here. So this would be your outer function here. This would be your inner. And what is the key when you use the key method? Isn't it pretty much always the derivative of the inner function? Almost always, anyway. And so what is the derivative of the inner function? Well, that's convenient because the derivative of the inner function is 2x, which is my key, and the key's there. It's perfect. So what do we do when we find keys? We check it off. We get excited that it's there. It is never, ever part of the answer. Never part of the answer. What is the key? It's permission. Permission to do what? Integrate one function and one function only, and that would be the outer function. So let's do it. Permission granted. Go ahead and add 1 to the exponent. Now, if I add 1 to that exponent, negative 4 plus 1 is negative 3. Divide by the new exponent, negative 3. The key is never part of the answer. Say goodbye to the key. And that's the answer. Well, here's a much better version of that. Nope, that's not right. Sorry, guys. I made a mistake here. This should be a 1 on top. I apologize. The 3 should stay right where it is. I made a pretty common mistake. Don't make that mistake yourself. And that is, I moved this to the bottom. That is correct. I should have moved that to the bottom. And it looks like I just moved that to the top. You can't do that. You can move the minus sign to the top, but you can't move the 3. The 3 is okay right where it is. Leave it right where it is down there, 3. Okay, so we corrected that. Now don't forget, this is actually from the previous unit. There is another way to do this. If you push the denominator to the top, and the reason you might do that is because it's failing the three-step checklist right away. The denominator is not to the 1 power. It's a different style of problem, actually. Now, how do we integrate this using U substitution? Don't we normally select U to be the inner on the more complicated? This one right here. And don't we always go to autopilot here? du dx is 2x. So we move the dx to the other side. And what's next? Substitution, full and complete. From now on, this is u to the negative 4. And always, always box this up and go hunting for that box. And we're in luck today. Look at that. 2x dx, just du. Couldn't be really an easier integral. It's integrate u to the power du. That's all it is. So let's do it. Add 1 to the exponent. Divide by the new exponent. This belongs down below. The 3, don't move it. It's happy where it is. But the negative factor can go upstairs. The negative 1 goes up there. Now, we started with x's. I need you to finish with x's. And you'll notice nothing has changed. The same answer. So I think we went through that just to show you that you've got to be careful. You can't really believe that all fractions integrate to become natural logs. It's just not true. Okay? The only ones that really integrate to be natural logs, three-step checklist. Number 1's fraction. We knew that already. Number 2, denominator to the 1 power is big. That's important. And number 3, the derivative of the bottom has to live on top. Without all 3 of these, you're really not going to produce a natural log. Let's take another one out. This one sends us down a very interesting road. want to integrate this fraction. Okay. Seems reasonable enough. And I'll pretty much always go after this with the three-step checklist first. I might use substitution on it, but I'm trying to see if this is going to be a natural log. Number one, is this a fraction we're trying to integrate? Yes, it is. Number two, is the denominator to the 1 power? Yes, it is, actually. Check. And number three, does the derivative of the bottom live on top? Not even close. We don't have a 1 on top. We have a quadratic up there. Now, if there was something other than a 1, let's say there was a 2 or a 9 or a 10 or some constant, we can make that a 1 by dragging the constant across the integral symbol, and it'll leave the 1 behind, so that would have been fine, but not a quadratic. Can't do that. So, no. Failed the three-step checklist, and there's no way to really modify the numerator to make it look like the number 1. So for the moment, you might think we're trapped in a corner. Notice that the degree up here is equal to 2, and the degree down here is equal to 1. When the degree is higher or equal in a fraction, you can actually just divide it out first. Now, wouldn't it be really nice if I chose one that was factorable? Yes, that would have been great, but that would be too easy. Now, if it was factorable, you would have x plus 1 factoring and canceling with that one, and it would have been a much easier problem indeed. It wouldn't even be a fraction. No, I chose one that you have to do this technique first. Let's do algebraic long division. So no calculus yet, please. No calculus at all. What is it when we divide x squared plus 2x plus 4 and you divide into x plus 1? What do you get? Well, this is what algebraic long division looks like. You make your quotient symbol. A couple of key things to remember is you want to make sure it's in descending power order, highest powers all the way to the constant. You also want to put in placeholders for the numerator that becomes the divisor. So let's say, for example, this said x squared plus 4, and this wasn't here. What would you put here? Well, I do want to see all the powers of x, so I have to put something in there for x. And what I would put here is x squared plus 0 x's plus 4. You got to tell me how many x's you have. So descending power order, and for the divisor down here, you want to really visually see each power of x. And if you don't have any, then you write 0x or 0x squared or whatever it is. Now, how does long division actually work again? What's the first thing you do? And that is a clue. It's first over first. And that's the only division you'll ever do. So first is x squared from here divided by first, which is x from here. And I got an answer. Now, where does my answer go? Up here on the answer line, right above my x's. Next step, prepare to subtract something. What are we subtracting? It's this times that. So x reaches out times x, x squared. X reaches out times 1. And now I need you to follow through with your subtraction and do it correctly. X squared minus x squared is 0, and that is by design. That first one should always be 0. But watch this one. See, if you look at it too quickly, you might think 3x. I get that, but the minus actually comes over and touches that, so it's 2x minus 1x. So that's x. And then the 4 drops down. If you can do that, you can do any long division problem because it's pure repetition after that. So let me review. First divided by first, answer. Answer goes up on the answer line. Then you take just that one part of the answer you just got, multiply by that divisor, and you subtract that whole thing in a set of parentheses carefully. Okay, I did say the rest is repetition, so keep going. Do another first over first. First over first will be this first x divided by this same first x. That same over same is 1. You just got an answer, so that answer belongs on the answer line right here. Okay, prepare to subtract something, and the something will be the answer part you just got, the 1 times the x, and the 1 times the 1. Now follow through with your subtraction. X minus x is 0, and 4 minus 1. See, 4 minus 1 is not 5, it's 3. And this, of course, is your remainder. So let me express what this fraction is, actually. So apparently, this fraction, which we call an improper fraction because it can be divided out, equals the answer on the answer line that you just got plus the remainder. There were 3 units left over that just wouldn't divide into my divisor, x plus 1. We always write the remainder over the old divisor or denominator. Okay. No calculus in that. That is long division and something you can look up if you want to do some more practice on it. We also have synthetic division when you divide by linear divisors like x minus k. You can use synthetic if you want as well. Now that we've rewritten this fraction as this expression where we have our answer plus our remainder, they're supposed to be equivalent. Therefore, I should be able to replace this entire fraction with that. Let's see what happens when we do that. Okay, so this entire fraction gets replaced with x plus 1 plus 3. But only the 3 is over the x plus 1 over there. So sometimes, particularly when the degree on top is equal or higher than the degree on the bottom, sometimes we have to divide first. And now we can integrate. Now the first two are not very difficult to integrate. In fact, let's do each one separately. Integrate the letter x dx, integrate the number 1 dx, and finally integrate 3 over x plus 1 dx. Well, don't forget to actually integrate. This was just algebra here. You've got to still do the calculus. X squared over 2, we know that. Matter and antimatter cancel. We just get the letter x. And what about that one? Well, that's why they introduced this in this chapter, because the 3 is going to come out. We know that. Do we need U substitution on this guy? I don't think so. Number 1, fraction, yes. Number 2, denominator to the 1 power, absolutely. And number 3, does the derivative of the bottom really live on the top? What's the derivative of this x plus 1? Isn't it 1? That's a big check mark. If you use the 3-step checklist, please don't forget the payoff. The payoff is, if you really check them all off, the answer will be the natural log of the denominator, plain and simple. So what's a better way to write this? To me, that's probably the best way, most compact way to write that answer. Now, we do need the protection of the absolute value. There's no question on this, because x plus 1 has the capacity to be negative. It would have to be like x squared plus 1 that would force it to be positive without the absolute value. Okay. Now, I did say that it seems like when you do U substitution, it seems like the rule is that U equals denominator. But when we do it for logarithms, when we do it for just the regular U substitution, that's simply a guideline. It might not work. You might have to try something different. So try it. If it doesn't work, try something else. If that doesn't work, try something else until it works, right? But U equals denominator is a guideline. U equals inner is another guideline. They're guidelines. They're not really rules, actually. It might not work. So I have a problem where the guideline fails us. Let's talk about this problem right here. It's an unusual little problem, because it already has a natural log in it. So let's go through the 3-step checklist. Number 1, Fraction, yes. Number 2, denominator to the 1 power, sure, why not? Number 3, does the derivative of the bottom live on the top? Not even close. Not even close. If you take the derivative of the bottom, it's going to require a product rule, right? And f prime g plus fg prime, it's certainly, I don't think it's going to be worth 1 like that. So I don't think that's going to work. I don't think we can fix it either. So what's the other way to do this? The other way is say u equals denominator. Maybe. And we got to do du dx. Okay, well, f prime g. So f prime g plus f and g prime. You know what g prime is? That's the derivative natural log. So it's an interesting little result. So du equals the natural log of x plus 1. The 1 is not inside the natural log. Maybe we could show it that way. And then here's our dx right here. Okay, let's try our substitution. Try it. Don't force it to work. You chose x, natural log of x, to be your letter u. That's fine. And look at this. What's left is simply dx. It's just a dx that's left, and I got to replace that dx with something that has a u in it. Oh, boy, how can we do that? Well, here it is right here, guys, dx. And maybe you might think of isolating it like this. Not such a bad idea. So here's what I got. Dx equals du over natural log of x plus 1. That looks pretty messy. So you mean to say that I have to replace dx right here with that mess right there. Why won't I do that? Number 1, it's just not going to fit our pattern. But most importantly, it has an x in it. You're not supposed to be left with x's. You're supposed to be completely in the world of u. So I don't think we're going to put that in there. But maybe we can fix this. Maybe we can write this without an x. Let's try it. Hey, remember u equals x ln of x? ln of x, what are you worth? Isn't that crazy? You're worth u over x. So here's another version that still doesn't work. ln of x, another version is u over x, apparently. And I'm still stuck with x's. So that's just not really working. See, while that looks pretty good, it's just not working because the end result should be du over u. And it's not looking clean at all, is it? So that's just not working. So like I said, guidelines say u equals denominator. Doesn't mean it's always going to work. Time to try something new, guys. Well, you got 2 choices. You could either say u equals x or u equals ln of x. I don't think u equals x is going to do us any good because u equals x, nothing changed, really. U and x, same thing. So the whole problem will be just written with u's. That's the only difference. But I don't think it's going to help us. So why don't we try u equals ln of x? Just a thought. Autopilot. Du dx is the derivative of natural log is 1 over x. Move the dx to the other side. Du is 1 over x dx. Okay, time for the full and complete substitution. Okay, let's see. You said from now on, wherever you see ln of x, which is right here, you're going to place a u. Well, wait, let me rewrite this first. In fact, I'm going to just use the commutative rule down there for a moment. That might help me. Commutative rule, of course, you can do that if you want to. The reason I did that is because from now on, we know exactly what ln of x is supposed to be written as u. Box up what's left, guys. Box it up and go hunting for that box. And there it is, over sitting in the derivative, a perfect copy of that box. Looks perfect, 1 over x dx, 1 over x dx. It's just du itself. And that makes me very happy because we know the answer to this problem. The answer to the integral of 1 over u is the natural log of the absolute value of u plus a constant. And what was u to begin with? We go back and find out. We chose it to be ln of x. Now, there is a difference here between these natural logs. One you did not produce, and I would just use the argument in its original form, ln of x. That's the way it was written in the original form. That's the way it stays. The other natural log you produced, part of the integration process, that's the one that requires the protection. I wonder if this works. You know how to check the result, right? Let's do it. Okay, let's do this, guys. Chain rule. Check off the natural log. What do you do when you take the derivative of the natural log? Isn't it true that it's 1 over the argument? And I do mean the whole thing. Okay, move on. What's the derivative of this natural log? That's the next function in line. Isn't it the derivative of its own argument, which is 1 over x? And finally, the derivative of x is just 1. And this, is, of course, is plus 0. So look what we found. There's the original problem back. We found it. Okay, now I know we've done a lot here, but I do need to finish up. And I want to look at a couple of trig functions before we really wrap this up. In particular, I talked about integrating sines and cosines and secant squareds. We can do all that, right? Because we know the derivative of secant squared is tangent, so the integral of secant squared must be tangent. But what's the antiderivative or integral of tangent itself? That one you have to think about. It says, I'm thinking of an original function whose derivative is tangent. What function am I thinking about? In reality, I don't know. I don't know a function whose derivative is tangent. I don't know that. Derivative of sine is cosine. Derivative of cosine is minus sine. Derivative of tangent is secant squared. And the derivative of secant or cosecant, they're not tangent. So derivative of what makes tangent? We don't know. What if I broke this up using the quotient identity in trigonometry? The quotient identity says that tangent is exactly the same as sine over cosine. That's just the quotient identity, trigonometric identity for tangent. Well, something very interesting happens. The first thing that happens is, number one, yes, you now do indeed have a fraction. Number two, the denominator is indeed to the 1 power. That's true. And number three, does the derivative of the bottom live on the top? Wow, close, isn't it? We can fix that, can't we? Put a minus here and a minus here. And now I can check number 3 off. Pretty impressive that when you take tangent, rewrite it using sine over cosine, all of a sudden it passes the 3-step checklist for fractions perfectly. So don't forget the payoff. When you do pass the 3-step checklist, by the way, the minus is along for the ride, the answer is the logarithm of the denominator, plain and simple. And we put protection in to protect the logarithm from taking the log of a negative number. Now, there are actually 2 potential answers for this. But isn't that a crazy result? The integral of a pure trig function becomes a logarithm. It's crazy, but it's absolutely true. Another version of the answer, you could take the -1 and plop it right up here. And what would that do? What's the -1 exponent? Isn't that a reciprocal, meaning it goes downstairs here? Who remembers what 1 over cosine really is in terms of its own trig function? Isn't that secant? It is secant. So it seems that they mostly use this one when we look up the tables for integrating tangent, but certainly that's got to be a valid result as well. Now I'm running out of time, but I'd like to look at the 6 trig functions and their antiderivatives. Let's start with the antiderivative of sine. Remember, everything's backwards. The antiderivative of cosine. The antiderivative of secant squared was a very popular one because I know the derivative of tangent becomes secant squared, so the antiderivative must be tangent. And now we've got a couple of new ones. So apparently in the tables, they like to use minus the natural log of the cosine. And then there's 2 more. And that would be secant and cosecant. Now, for those, it's much more involved, but we again apply some identities to get this to look like a fraction. And you'll pass the 3-step checklist, and you ultimately land on this crazy result. And then cosecant should be somewhat similar. The integral of cosecant is so, I guess there's one more, which is cotangent, which should be very similar to the tangent, because this one would be cosine over sine. And we can actually do that one ourselves. Let's do that one ourselves. Number 1, check. Number 2, denominator to the 1 power. Yes. Number 3, it's perfect. Derivative of sine is cosine. Jump directly to the answer, the natural log of the denominator. Don't forget the payoff, please. So that's the antiderivative of cotan. So if you want to see the proofs for those other functions, you can look in the book, page, 332 shows the proofs for the cosecant and the secant. It gets kind of involved, I've got to admit. I'm not going to ask you to necessarily prove those. But I do need you to know now the integral of tangent and cotangent are pretty important now, and they are natural logs. So thanks for sticking through this video. A lot to consume. And we'll continue on with exponentials next. Thanks.